Hi, everybody. I hope you're doing well. I want to start by describing the theory behind the experiment that we're going to look at today. So hold on one second, and I'll go through some slides. By the way, everything I'm covering here is also covered in the handout for the lab. Very good. So today we're going to investigate a diatomic molecule, diatomic iodine, okay? And in diatomic iodine, we have two iodine atoms that are bonded together with a covalent bond. What we learned in class is that if we disturb this system, we can get vibrations because the force between the two atoms can be approximated as the force due to a spring. This is called the harmonic approximation. And we found that we got quantized vibrational energy states, a quantized harmonic oscillator. Okay? Now, in the experiment we'll do today, we're going to excite this molecule with a laser, and then we'll observe fluorescence when it relaxes, okay? Just to sketch out what's going on, we can imagine that in its ground electronic state, the system looks like this. So this is a graph of, in green here, of energy versus interatomic distance for the ground electronic state. And it looks kind of like a parabola, at least close to the minimum. And as a result, we expect to see quantized vibrational states that are approximately equally spaced. Now, if we excite the molecule with enough energy, we can excite it into an excited electronic state, like this one. In that case, one of the electrons has gone into a higher orbital. Molecules have electronic orbitals just like atoms do. Okay, and so the excited state also has vibrational levels. Okay, in our case, we're going to excite the molecule from initial state up to an excited electronic state, and then from there, it will drop down into various vibrational states associated with the ground electronic state. Okay, and from that, we'll be able to study the spacing between the vibrational energy levels. That's really the goal of our measurement. These kind of transitions where we change both the electronic and the vibrational quantum numbers are called vibronic transitions. So this is vibronic spectroscopy, a great word, I think. Okay. So to begin with, we can approximate the potential between the two atoms as harmonic. If we do, we're in the harmonic approximation. And in that case, we know that the energy level should be equally spaced. E sub n should be n plus 1/2 times h bar omega naught, where omega naught is square root of spring constant divided by the reduced mass. That's all familiar to us. And that's basically what we expect to see, nearly equally spaced energy levels. However, if our experiment is accurate enough, and if we see data from high enough vibrational states, we should start to see a deviation from this approximate form. Because when we go to higher energies, the potential is no longer really parabolic. And so we expect that the spacing between the energy levels will no longer be equal. Chemists like this model called the Morse model. This potential here is an example of the Morse model. In the Morse model, the potential energy is D times 1 minus e to the minus ax, and then this entire term is squared, where x is the distance between the internuclear separation and the equilibrium internuclear separation. This model gives the following energy levels. This is why it's so great. E sub n is equal to n plus 1/2 h bar omega. Okay, well, that's what we just had before. Minus another term, which is just n plus 1/2 squared h bar omega times b, where b is a constant. So you can imagine that this is just like a correction factor Okay, so the Morse model gives us a second order correction factor to the energy. In any event, there's a correspondence between the Morse model parameters D and A and the these terms, h bar omega naught and B, and those correspondences are given here. In our case, we're really interested to know h bar omega naught, that's the line spacing in the harmonic approximation, and we're really interested to know the dissociation energy, D sub E. The dissociation energy, you can see, is how much energy we have to add to the molecule before it breaks apart, before we put it into a state where the two nuclei can be infinitely separated. Okay? All right. And so those are the two things we expect to get from our measurement. How does our measurement work? Well, we have an iodine cell, which is filled with gas, with iodine vapor, and nothing else. It's going to be excited with an argon ion laser, a bright green beam at 514.5 nanometers. The radiation will come out of the laser. It'll be directed through the cell. We'll also go through a bandpass filter that knocks out any light from the laser that's not at this wavelength. And then the laser will proceed and be stopped by a beam block. The laser radiation will cause the iodine to fluoresce. We'll talk about that in a second. The fluorescence radiation will go out in all directions. Some of it will be captured and collimated and then focused onto the end of an optical fiber. And the optical fiber will lead to a small spectrometer, which will let us measure the fluorescence spectrum of iodine. It's all very nice. And now it's interesting to look schematically at what we're doing when we do this experiment. The system is starting in some initial state, and then the laser is exciting it to some excited state. This is one of the vibrational states associated with an upper electronic state. We don't really need to know the details of this upper electronic state, okay? What we're interested in is the following. When the molecule de-excites and drops back down to the ground electronic state, it can end up in any of the different vibrational states. So we expect to see a series of bright lines or fluorescence lines in the spectrum, emission lines. And they'll correspond to transitions from this excited state to each of these vibrational states, okay? What's neat about this is that if we measure the separation between between the emission lines, that's just measuring the separation between the vibrational energy states. Okay? Okay, well, that's all I wanted to cover. There's some more details that you'll find in the handout, but I wanted to give you a basic idea before we start talking about the equipment. All right, let's stop here.